In section 5.1, we're talking about how to find the area under a curve, but we're going to be doing it with a certain approximation method. We're going to be talking about how to approximate area with rectangles. We don't yet know how to do antiderivatives for all types of functions. So first concept is talking about distance traveled, and it says explore the problem. A train moves along a track at a constant rate of 75 miles per hour from 7 a.m. to 9 a.m. What's the total distance traveled by the train? And if you recall, distance equals rate times time. So if you were to actually sketch a picture of what this function might look like, this train is like in utopia here, perfectly constant rate of 75 miles an hour. What an amazing train that is. And it starts at 7 a.m. and goes until 9 a.m. So if I wanted to find the area, oops, I missed my 9 a.m. The shape of that graph is obviously a rectangle. And so to find the area of a rectangle, we're going to do length times width. So in this case, the length of the rectangle was 2 hours. And the height of this rectangle was 75 miles per hour. So when we multiply these two things, 2 hours times 75 miles per hour, obviously the hours are going to cancel out, and 2 times 75 says that the train is going to travel 150 miles. So the same type of thing applies with example 1. And it says we have a particle that starts at x equals 0 and moves along the x-axis with a velocity of t squared. There's my favorite function, that lovely parabola. But we're talking when time is positive, and they want to know where is the particle at time 3. So they're not asking what the velocity is at time 3. They're asking for a position or a displacement here. So when I look at the graph of this function, it starts at 0, 0. And at time 3, it's up at 9. But then we've got to have a couple of markings in the middle. So if this was 9 up here, 1, 2, 3, 4, 5, 6, I missed 7, 8, 9. So I'll move my point up a little bit higher. At 1, we're going to go up 1. And at 2, we're going to go up 4. So we get this nice parabola. Now we don't have a geometric shape for a parabola. So what we have to do is approximate this area underneath the curve. And we can do it in one of 3 ways. You'll see that they mention this rectangular approximation method up here. When we do a rectangular approximation method, there's 3 ways we can do a rectangular approximation. We can use a left endpoint, a right endpoint, or a midpoint. And so you'll notice you'll see these abbreviations, LRAM, MRAM, and RRAM. So I want to start with pencil. I'm going to do the left-hand approximation. We're actually going to calculate all 3 of these. So LRAM, MRAM, and RRAM. So the left endpoint, my first interval goes from 0 to 1. The left endpoint is at 0. The function is at 0. So I'm going to draw the rectangle, and you should recognize there's no rectangle there. The next interval goes from 1 to 2. That rectangle goes up 1 and over 1. So this is a 1 by 1 rectangle, obviously not drawn to scale. So the area of this rectangle, we have 0 and 1. I'm going to keep track over here. From 2 to 3, the left-hand endpoint would be at 2. At 2, it goes up to 4. If I plugged 2 in, I get 2 squared, which is 4. And if I draw that rectangle, 4 times 1 is 4. So here we're saying that the area under that curve is 5. As you can see here, we have a ridiculous amount of underestimation here. I've got lots of area underneath that's not being touched. Now I'm going to grab a second color. With my second color, I'm going to use red. I'm going to do the right rectangular approximation. Exact same method. So still I'm looking 0 to 1. The right hand endpoint is at 1. But now I have to draw my rectangle kind of backwards. So now my rectangle is up 1 and over 1. So that one had an area of 1. My next rectangle from 1 to 2, the right hand endpoint is at 2, so still using this line. I went up 4, but I draw it back. So the area of this rectangle is 1 by 4, which is 4. And then from 2 to 3, my endpoint at 3, it's going up 9. And so this one is 9 by 1. So when I add all of these together, I get a total area of 14. And as you look at this one, you can see, whoa, Mrs. Meyer, there is a lot of overestimation going on here. So now we take out a third color, and this time we have to use the midpoint. So for midpoint, I'm going to use purple. So still looking at the same areas here, so from 0 to 1, the midpoint is actually at 0.5. So I'm going to go to 0.5, and this time I have to draw the rectangle to the left and to the right. The problem is I don't know how tall this rectangle is. It's still a length of 1 times this height. This height happened at 0.5. And so if I plug in 0.5 squared, I get 0.25. Now my next rectangle, from 1 to 2, the midpoint would be at 1.5. And again, I draw all the way across. So this time I have to do 1.5 squared to figure out how high I went. And still a length of 1 on this rectangle. So 1.5 squared is 2.25. And then my last interval from 2 to 3, the midpoint would be here at 2.5. So the height this time, because this is t squared, I went up 2.5 squared. 2.5 squared is 6.25 for a grand total of 8.75. Now this one, you'll notice, has some over approximation but also some under approximation for each one. So in this particular model, we can guess that that MRAM is going to be the closest approximation. So when we actually do the real approximation, I'm going to show you how to do that. We're going to do something called an integral just to introduce it. And we're going to do the area from 0 to 3. It's this elongated S looking thing. And our function was x squared. And we're doing this area with respect to x. So on your calculators, you're going to go to FNInt, which is Math 9. You've been doing Math 8 for NDeriv, but FNInt. If you have a TI-84, you can just enter in the numbers as it is. If you have one of the 83s with the old syntax, then you'll have to enter in x squared, comma x, comma 0, comma 3. And if you actually plug that in, go ahead and FNInt it, you can pause it, but you should end up getting a total area of 9. So when you look at all of these, the MRAM was the closest approximation. Now what I want you to do is try this one, doing LRAM, MRAM, and RRAM. Notice you have a different function this time. I'll put the answers up in just a moment. All right, and there are the answers and some of the work. You can pause it to look at what I had to do to get those answers. Last but not least, the generalizations in here. The first one says if we have a positive continuous function that's increasing on an interval, what can we say about the sizes of LRAM, MRAM, and RRAM? So here's a picture of what's happening. If we have an increasing function that's positive and continuous, in this instance, we would be able to say that LRAM, wasn't bad, R, is smallest, MRAM is next smallest, and then RRAM is the biggest. And that would match up with what we talked about up here with x squared, small, medium, big. But if we have a positive decreasing function on a particular interval, that opposite will be the truth. So now our right approximation would be the underestimate and the left would be the overestimate. So we would have to flip that around. So RRAM would be the smallest, then MRAM, and then LRAM. Good work.